This is FRM Part 2, Book 1, Market Risk Measurement and Management, and the chapter on empirical approaches to risk metrics and hedging. What I want to do is give you guys a real basic example of hedging and how a perfect hedge works so that you get the sense of the imperfections that we're going to examine inside of these learning objectives in this chapter. So let's do a quick hedging example here. And I'm going to read some of these quickly and do the math quickly, and I think you'll be able to follow along. And I'll summarize it at the end, and that'll lead us directly into the hedges that we're going to look at in this chapter. All right, let's suppose that we're considering a farmer, and this farmer expects to harvest 10,000 bushels of corn in 3 months. So what kind of risk is the farmer exposed to? Of course, this is commodity price risk. The farmer will benefit if over those next 3 months the price of corn rises, because then the value of his harvest will increase. Of course, then the opposite is true. Let's take the extreme example. Suppose the price of corn in 3 months is $0, then the farmer has done all that work and gets no compensation. So farmers and lots of other investors are exposed to commodity price risk. One way to hedge this is by using a corn futures contract. We're going to see how this results in a perfect hedge. Let's suppose that the spot price of corn is $3 per bushel, and the 3-month futures price is $3.25 per bushel. And let's really not worry too much about the difference between those two and the basis and spot supply and demand and futures supply and demand. Let's just take those as given. Now, when the futures price is $3.25, what that implies is that the farmer agrees to sell his corn in the futures market for $32,500 Now remember, the farmer's selling 5,000 bushels of corn. 10,000 bushels of corn. The standard contract on the futures exchange is 5,000 bushels, so the farmer will need 2 contracts, right? 10,000 divided by 5,000. That's going to be an important number when we work through the example inside of this chapter. All right, so how does the farmer hedge? The farmer is naturally long in the spot market, right? Because he or she benefits when the prices rise. And so the farmer will take the short position in the futures contract. This is how you hedge. You have one position in the spot market, and then you have the opposite position in some other market. In this case, it's a derivative security, the derivatives market, and it could be almost anything. We'll see that as we go through the chapter. Now, this perfect hedge relies on the concept of convergence. Let's go back up to those 2 prices. So the price of spot price is $3. Futures price is $3.25. And what do we know? We know that those 2 prices, here, let me do it like this. Those two prices, here's the spot, here's the futures price, they're going to change over time, right? And they're probably going to go together, right? It's a derivative market, so the value in the futures market has to depend or is derived from the value in the spot market. So they're going to fluctuate, pretty much in tandem, maybe not 100%. But as they get closer and closer to the maturity date of the contract, those 2 prices are going to get closer and closer to each other. And exactly on the maturity date of the contract, those 2 prices will converge, because the spot market and the futures market are essentially the same market, right? In the futures market, you may agree to buy or sell in the next minute. Well, that sounds an awful lot like the spot market. So those prices will converge. All right, so what I want to do quickly is I want to skip ahead to the maturity date of the contract. Let's forget about all the marking to market that the futures markets require. Let's suppose that the price of corn, and this means both the spot and the futures price of corn, will be $4 because of convergence. So that price is $4. What will happen? The farmer will go to the spot market and sell his or her bushels of corn, 10,000 times $4, and receive $40,000, right? This is good news for the farmer in the spot market. But since the farmer was short in the futures market, there's going to be a loss, right? So what is that loss? Look at the math quickly there. There's the $3.25, subtract out the current price of 4, multiply by the standard amount, 5,000 times the 2 contracts. That gives us $7,500. So if you net the 75 and the 40, you get total proceeds from the sale, $32,500, which is exactly what we suggested up at the top of the slide. Now let me just quickly show you what happens if the price of corn falls. So notice part B, I say, suppose the price of the corn falls to $2. Well, this is bad news in the spot market. So the farmer's only going to get $20,000 from selling his or her corn, but there's going to be a gain in the futures market. So look at the gain there, 325 minus the 2 times the 5 times the 2, that gives me 12,500, and that gets the net proceeds up to 32,500. So this is a perfect hedge. It's called a perfect hedge because no matter if the price of corn goes up to $4, to $5, to $6, to any number, no matter if the price of corn falls to $3 or $2 or $1, that outcome is going to be $32,500. This is a perfect hedge because the farmer is locking in that future net selling proceeds of his or her corn. Now remember, the goal of the hedge is not to make a profit. The goal of the hedge is to lock in a future value. And that's an important concept. So let's look at these learning objectives for this chapter, and I'll refer back to this quick example so that you get a sense of the imperfections in the fixed income market and the inability to arrive at a perfect hedge. Because in this case, we had corn in the spot market and corn in the futures market. So the two assets were identical. And we were harvesting the corn on the day that the futures contract matured. So the asset and the timing matched. That's why we were able to arrange a perfect hedge. Now, when we buy bonds, we have all sorts of risks. You know, commodity price risk can pretty much be summarized by the relationship between those two prices in convergence. But with investing in fixed income securities, you know, we have credit risk, we have interest rate risk, so we need to worry about duration and convexity. We might have liquidity issues, we might have currency issues. So all those things are going to contribute to our inability to get a perfect hedge. But what we're trying to do is we're trying to arrange that perfect hedge. You know, I always tell my students this, look, if you don't have the futures contract, you have this much volatility. And in this case, the perfect hedge gets us down to zero volatility, right? The 32,500. But with imperfect hedges, we're going to get a vice and we're going to squeeze and squeeze, and we're not going to be able to squeeze any further. But still, this variability is better than this variability. So this is a hedge, this is not a hedge. My children say I'm terrible at charades, but I think that was a pretty good one. All right, it's been a while since we've had a learning objective action word that says something like calculate. So we're going to do a couple of calculations and some examples, but we're going to look at this. We're going to look at a neutral hedge. We'll look at a recession hedge, and then we'll do some PCA at the end. Let's go ahead and remind ourselves about this dollar value of a 1 basis point change. And so we have a fixed income security, right? We know that if interest rates rise, the bond price is going to fall and vice versa. And so, you know, the smallest change that we're interested in is 1 basis point. So that's, you know, 0.0001. And so we're asking ourselves the question, if the yield on our bond goes up by 1 basis point, we know that's bad news for the bond price, but we want to know, how bad is that news? Is the bond price going to fall from 100 down to 98, or is it going to fall from 100 down to 92? I mean, this is a big deal. So the DV01 helps us determine the sensitivity of our bond price to changes in yields. And there's a formula that we've seen sometime in the past. All right, let's go ahead and start with a standard hedge. And let's swing back to my example of the corn. What was our standard hedge? Our hedge ratio was the spot, which was 10,000, right? We had 10,000 bushels of corn. And the standard amount of the futures contract, that was 5,000, right? So we had 10,000 over 5,000. So we had two contracts. So we're really going to be interested in what is that optimal hedge ratio, because what we want is we want the performance in that hedge asset to exactly offset the changes in the spot asset. Now notice back in that perfect hedge, because of convergence, we had an exactly one-to-one relationship, at least as it approached maturity. But of course, that's not going to happen in the fixed income world. And the reality of life is that the one-to-one relationship between the yield on the spot instrument and the yield on the hedging instrument is probably not going to be one-to-one. Now, what we're going to do in this example today in the slide deck, which mirrors what goes on in the chapter, is that we're going to consider a treasury bond, and we're going to hedge that with treasury inflation protected security, TIPS. And so notice the difference between the nominal yield and the real yield. And so, boy, what did we have earlier? Spot and futures price of corn, they were pretty much moving in tandem until they converged. But how about those two yields? Are they going to move in tandem? Well, they'll probably move somewhere in the same direction, but probably not one-to-one. Of course, it's not going to be perfect. Now, one of the questions that we can ask is, hey, let's go back and see what those yields have done over the years. So historical evidence strongly, notice I have that word strongly in there, suggests that nominal yield adjusts by more than 1 basis point for every basis point adjustment in the real yield. And that probably should make some basic fundamental economic sense. What we're going to do is we're going to use some regression analysis techniques to make adjustments to that standard hedge. That standard hedge was just the 10,000 over the 5,000. Then we'll use our statistical friend, some regression analysis, which ultimately is going to result in a regression coefficient. Remember, that's going to be beta. And I had a great professor when I was in graduate school who gave us example after example is to think of beta as just a measure of sensitivity. How sensitive, right? If the beta is 0, then boy, we really don't know what's going to happen. But if the beta is really high, that means that it's highly sensitive. All right. And then the regression hedge is probably going to be exactly what you might suggest. You know, there's a little picture of the plot, and then remember that least squares method. What it does, it minimizes the distance between each of those possibilities on the curve, each of those plots on the curve, and a line. That's why it's called the least squares. And so we're going to use that beta as a measure of sensitivity. So imagine, you can look there and you can see that each of those dots is about, it's about 1 unit away from the line. But suppose those dots were, 4 or 5 units. So 1 was way up here and 2 was way down there, et cetera, et cetera. Well, then that would result in a much different beta. All right, so here's an example that's pretty similar to what goes on inside of the chapter. So here we are. We had to pick a date, so let's pick May of this past year, 2019. And let's look at this just from the perspective of the short position. So we're going to short $100 million of 3.625 coupon rates of treasury bonds that mature in August of 2020. So if we have this short position, what are we betting on? We're betting that interest rates are going to go up, right? So that the price of the treasury bill goes down. So what are we exposed to? We're exposed to interest rate risk. That makes perfect sense. No credit risk because these are treasury securities. All right, let's layer that with another security, but instead of really worrying about interest rate risk in general, let's look at one of the components of interest rate risk. Let's look at inflation. And so let's go ahead and offset that short position by buying some of these tips. So we have a coupon rate that's about half, but it matures somewhere around the same day, July 15th, 2020. And remember, these tips are going to make inflation-adjusted payments. So if inflation spikes over the next year or so, then we're going to get a higher coupon payment, right? And what we're going to do is we're going to use that long position in the tip to hedge the treasury bonds. So now do you see what's happening here? Now our bet is not on interest rate risk in general. Our bet is on the rate of inflation over this next year and a half or so. And that spread between the nominal and the real securities is going to reflect current views on inflation. So what we're trying to do is we're trying to say, look, here we've got this investment. We want to kind of lock in a future value. We want to lock in a future value, and we don't really want to worry about interest rate risk, but we might want to be exposed to rates of inflation. Notice what I have in that third block point. Over time, changes in yields on nominal bonds and the tips do not move in line. The changes do not track one-to-one. So that should make perfect sense given the context of our corn example. All right, so let's take some historical data for yields and the DV01s on these two positions. And so here's a summary table. We have yields of 1.2 and 3.2 on the tips and the treasury bond. And then that dollar value is 83 and 67. All right, so here's the first question, which was identical to what we asked back in the corn example. We have 10,000 divided by 5,000, so that was 2, right? So that was our hedge ratio. Well, here, all we're going to do is take the ratio of the dollar value of each of the O1s, and we'll take the nominal bond, the treasury bond, put that in the numerator, divide that by the tips. So 67 divided by 83 gives me about 80%. So that makes sense that if the face amount of those treasuries was 100 million, and those treasuries, right, those treasuries move like this. Let me do it like this. Those treasuries move 67, right? But the tips move 83. So we're not going to need as many tips to hedge the 67s. So we're really only going to need 80%. So take the 807,229 times the 100 million, and that gives me the face amount of those tips, 80,722,891. And so do you see what's happening? We got one thing doing this, we got the other one doing this, so we need less of the hedging instrument so that we can try to, right? We're trying to put us into a vice and squeeze down. We're not going to get to this point, right? We're not going to get to this point because of the bet on inflation, but we're going to get to this point. Now, of course, that's not a perfect hedge. So the question is, can we hire somebody to come in with big muscles and turn our vice so we can squeeze it a little bit closer together? And that big muscular person, of course, is going to be regression analysis. So what we're going to do, notice that the independent and the dependent variables are delta y. So we're going to look at the change in the yield to maturity on the real and the nominal securities, right? And then we're going to just do our regular old least squares regression, and then the beta term in the middle, that's our measure of sensitivity. So look at the bottom block point I have. It paints a more realistic picture than does that simple standard DV01 based hedge. Sometimes this is referred to as kind of a naive hedge, and so the regression analysis layers this with measure of sensitivities over time, and that's captured by slope. All right, so here we are. There's our same table, but let's suppose that we run this regression analysis and we get a beta of 1.0165. All right, so all we're going to do is the same thing. There's the face value. There's our hedge ratio. So the 67 divided by 83. And then we're going to adjust that by the beta of the 1.01. Did I get all those decimals in there? Yeah, 1.0165. And that gives us 82,000. So here, where was I back here? Here, we went like this and we squeezed it down. We got to 80,000, and we're going to squeeze it a little more by taking a long position in those tips of another what was I think I was saying 8,000, I meant million. So instead of 80 million, we're going to do 82 million, an extra 2 million, and that's going to squeeze that variability. We're never going to get to this, right? We're never going to get to zero variability. That only happens in a perfect hedge, but we're trying. And of course, traders are on the lookout for extra muscularity in getting that vice all the way, as close as possible. But because of the complexities of fixed income security valuation and durations and convexities and all those things that I talked about earlier, we're probably not going to get all the way down to zero. Although I will say this, look, back here in this example, where was I? If we were shorting 100 million and we wanted to completely eliminate interest rate risk, we could just take the long position in a treasury bond futures contract. That would get us all the way down here. I could show you an example where you could get pretty close to zero, if not exactly zero. But that's not what we're doing here. We're trying to make a bet on inflation. All right, so let me scroll back here. I put this slide in because the chapter has a really cool example about volatility. This is not one of those learning objectives, but I thought I'd go this just quickly so that you could see exactly how cool these DV01s are and what we've done. So, of course, what we're going like this, and we're not getting to this point here, so we're not going to have a standard deviation of zero. We want to know what that number is. And here it turns out to be $193,000. So the standard deviation of the portfolio, and I made up a number there, standard error of the regression is 2.89. And you get that from any simple software package. And so you use that formula there that's taken right out of the chapter. And so now you get a measure of how wide that range is. Now, again, that's not part of the learning objectives, but knowing that number and knowing what the next step is probably valuable information to be able to answer some question on the exam. Remember, I say this pretty regularly. When you go into that exam, you have a toolbox, and you want to be weighted down by that toolbox. You want to be able to not even walk to your seat. You got all these tools in your brain, and so this is probably another tool. Now, of course, you ought to be thinking, all right, Jim, we just did a simple linear regression. Does that mean we'll do multiple regression? And of course, the answer is yes. There are always scenarios under which you could come up with multiple variables to try to hedge some kind of a risk. And so here's an example. Let's suppose that we take a position in an interest rate swap. So remember what an interest rate swap is. All we're doing is agreeing to swap fixed for variable or variable for fixed payments, whether we pay the variable or pay the fixed. And let's suppose this is a 20-year swap. Right? Now, whatever we do, whether we're paying the fixed or paying the floating, we're exposed to interest rate risk. And so if interest rates move against us, depending on the notional principle of the swap, we can lose tons and tons of money. Oh boy, so what do you think? I mean, how do we hedge this interest rate exposure? Well, you might think to just take the opposite position in a 20-year swap, but that might not be practical. It might be too costly. Marginal benefits might not be there. And what might be more efficient is to combine a 10-year swap and a 30-year swap, right? 10, here's our 20, so we got 10 and 30. So those two things as a portfolio, they probably work pretty similarly to a 20-year swap. So this is what you can do. You can take the yields on the 20-year swap, put them on the left-hand side. Those are the dependent variables, and then the change in the 10 and the change in the 30-year swap. Those are the independent variables. And then you can come up with some kind of a multiple regression output like I have here at the bottom of the table. Let's go ahead and interpret these things. Notice that we're going to have two sensitivity coefficients, two beta coefficients, 22% and 77%. So this is what this means. We're going to hedge 22% of the 20-year swap with the 10-year swap and 77% of the 20-year swap with the 30-year swap. So we're going to take some proceeds, and we're going to put 22% in the 10-year and 77% in the 30-year. Now, of course, you should be thinking, all right, 22 and 77, they don't add up to 100, but they nearly do, right? They nearly do this. So once again, we're not going to get to zero, but we're going to get pretty close. And then, of course, if you look up at the R-square, 99.8%, that means that, we're explaining lots and lots of variability by those two positions. So this this hedge is probably going to get us pretty close. And so notice those sensitivities, those betas, the 22 and the 77, they help determine the hedge ratios for the hedged asset. This is cool. The simple regression model, that's pretty cool when you're hedging just one security with another security, like we did with the corn and like we did with that treasury bond. But that doesn't mean that you can't span the capital markets for lots and lots of other securities so that you can find the most efficient hedge. And this multiple regression analysis enables you to do it. All right, so there's a learning outcome that asks you to compare level versus change regression. So which one's better? Notice what we did earlier. We had the deltas, right? Delta Y and delta X, and we did all that kind of stuff. But what we could do is we could just regress yields on those two securities, the TIPS and the treasury bond. Which one is best? Well, both of them are going to have unbiased estimates of beta, and they're going to be consistent, but they're not going to be efficient because, and this is something that we've talked about in previous chapters, because remember that when you do this method of the least squares, you're assuming that stuff that happened yesterday is not really related to stuff that happened 2 days ago. So really, today's estimate is not independent of yesterday's. So we're going to have this serial correlation among the error terms. So we'll have to correct for it. And so we can use that model down there where we use the error terms in its own regression equation. So the learning objective doesn't ask you to do this method, but it asks you to probably understand it. All right, how about this one? What we've done so far is we've had one position and we hedged it with one position. We had one position and we hedged it with two positions. But let's suppose we have 100 positions. Or let's suppose that we have 10 positions and that those positions are functions of hundreds of factors. I mean, how do you deal with this? If you pick, can you guys see my hands up here outside of them drawing a big circle? How do you manage it when the universe of relevant factors is pretty gigantic? The simple example of this is, and we did this in the last chapter. We had this big old variance covariance matrix. So a portfolio of 100 variables is going to have 4,950 entries in that variance covariance matrix. The chapter calls this the curse of dimension. It's not too different from how I feel as a parent of all of these children. I'm trying to juggle. I have all these kids. I got to take them to basketball, one in college, How do you deal with all this stuff? And so what you try to do is you try to say, all right, let's look at the principal components. And one way to execute principal component analysis is to look at my life and say, okay, this is what I think is the most important thing about my children. Their grades, their performance socially, their performance athletically, how they treat their mother. All right, let's pick four of those. But what happens then is when you extract those important variables, you lose the correlation between and among all of those other relevant factors. So the other way to do principal component analysis is to leave all those factors intact and then perform some kind of tests so that you can see which ones are correlated with each other and then extract those groups of factors so that you learn from all of those. You don't eliminate those, you learn from those things. And that's what we do at the end of this chapter. So the example in the chapter, and that's what I use here in the slides, is let's suppose that you have a 30-year term structure and you're trying to price a 30-year swap or some other kind of interest rate derivative, and you have 30 factors, right? You have the 1 year, the 2 year, the 3 year, all those swap rates, and you can compute all those fixed swap rates, if you want to. You're probably better off using Excel to do all those. And so what we're saying is that we need to figure out of all of that term structure, which ones are important. Now, what we could do is we could just say, you know what, I think the 3rd, the 11th, and the 29th yields, swap rates those are the most important. And so you could take those out. But remember what I said, if you take those out, then you lose the relationship between the 3rd and the 5th, and the 12th and the 17th, and the 29th and the 31st. So here are the properties of those 30s. So of course, we're going to do something with standard deviation. So the sum of the variances of the principal components equals the sum of the variances of those individual rates. That's the grouping thing that I was talking about. Those principal components are not correlated with each other. And each principal component is chosen to have the maximum possible variance. So it's capturing all the stuff around it. So once we do all that, we really only need to describe some of those. We can find those principal components. And so notice what I have in the last circle point. The sum of the variances of the first 3 principal components might provide a good approximation of the sum of all the variances. Okay. Now, the point of all this is that given large sets of rates, think about 30-year rate, but go back to like that Walt Disney bond that was issued about 20 years ago. It was a 100-year bond, so it's still an 80-year bond. So you have 80 rates, 80 possible spot rates for this bond. So it's just way too complex to deal with all of those things. So notice what I say there in that first block point. Which factors are needed to hedge K% of the variance? And so what the chapter tells you is that, man, you can describe about 90 to 95 or 98% with those K% of the variables. Maybe it's 10%, maybe it's 20%, but it's not 100%. And so notice what I say. Notice what I say there in conclusion. We are able to focus on a few key risk drivers to hedge our exposure, right? Let me do this one last time. In fact, I enjoy doing this. We're squeezing and squeezing and squeezing. So we're trying to get all the way down to as close to 0 as possible, knowing that we can't get to 0. And I think that takes us through the slide deck.